Okay, welcome back. Sorry about the weird little pause there. I was just getting myself, my little technology straightened out here. So welcome back for another round of biology lecture. So today in biology, we are talking about chemistry. And that might seem a little strange, but it's important because if we want to understand the biochemistry of cells, we have to understand some basic chemical principles. And so that is what today's chapter is all about. So starting with section 2.1, we are going to talk a little bit about atoms and atomic structure. And of course, atoms make up all matter, not just living matter, but they certainly make up living matter as well. So this newt, this cute little guy, the leaves he's on, the air, everything, living, non-living, all forms of matter. It makes up every object and consists of one or more elements, which is a pure substance. So gold is an element, carbon is an element, hydrogen is an element. It's a pure substance of something. These objects are made of atoms that are organized into molecules. So an element, again, is a substance that cannot be broken down by chemical means into other substances. If you were to break it down, you would no longer have that substance. So if you took gold and you broke it down past the atomic level, you would no longer have gold. You'd just have some pieces of subatomic particles. So living things are primarily composed of just 6 elements. Whether we're talking plants, humans, newts, flies, we all are basically made of the same ingredients. And those are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So we're going to talk a lot about these elements, not so much about some of the other ones like, say, fluorine or gold, that while they're perfectly good elements, they're just not really found in biological systems, or they really shouldn't be. So we won't talk about them as much. So this little abbreviated periodic table shows most of the important elements in life. You can see, so the dark blue is the elements that are most abundant. So you can see our biggies, our carbon, our nitrogen, our oxygen, our hydrogen, and then we have, slightly less abundant phosphorus, sulfur, chlorine, potassium, calcium, magnesium. You might recognize these as things they put in vitamins and sports drinks. We also would refer to these as minerals that we need to get our body working properly. And then there are a few trace elements. Fluorine actually is one of them. So when I said there's no fluorine in a biological system, that strictly speaking was not correct. There is, it's just in very trace amounts, and too much would be toxic. Iodine, selenium, copper, zinc, nickel, these all are found in very trace amounts, but they do have important roles, and without them we could have problems. So what else do we see going on here? So each box shows an element, and they've kind of put a box to the side here. And so we have a symbol for the element, and they say C for carbon. It's either 1 or 2 letters, right? Here's a 2-letter one, Cl for chlorine. In this case, it says the element's full name as well, and it's 2-letter symbol. We also see the atomic number, which is this top number here, and the atomic weight, which is this bottom number here. So to understand what these mean, we first need to talk about the particles that make up an atom, the protons, the neutrons, and the electrons. So that's what we're going to talk about right now. So this is a drawing of an atom. Again, the smallest piece of an element that still retains the characteristics of that element. And it is composed of 3 smaller particles, the protons, the neutrons, and the electrons. So the electrons, whoops, having pen problems, the electrons are shown here. These little purple balls are representing our electrons. And you can see they're kind of, looks like they're swirling around, and that's because they are very small and they move very fast. and they are moving around this area called the nucleus. Now, this is not the same as the nucleus in a cell. This nucleus is made of two other types of subatomic particles, one known as the proton and one known as the neutron. And these aggregate together in the center of the atom, in the region is what we call the nucleus. Now, these subatomic particles have charges, or at least two of them do. So the electron has a negative charge. The proton has a positive charge. And the neutron is called the neutron because it's neutral. It has no charge. So the mass of a proton and a neutron is roughly equal. They have a mass of 1, and it is 1 AMU. I'll take this off. That's my little, be excited for chemistry. Okay, 1 AMU. Atomic, which stands for atomic mass unit, which is how we measure something that little. The takeaway here, basically, protons and neutrons have a very small but measurable mass. Electrons are so very small that for purposes of this class, we can consider them as having no mass at all. So back to our symbol here. The atomic number indicates how many protons are in an element. Carbon has 6 protons, so the atomic number is 6. The atomic mass is determined by the protons plus the neutrons. So the mass number of the carbon atom is 12 because it has 6 protons and 6 neutrons. So that's how we get that number 12. So usually, not always, but usually the number of protons is the same as the number of neutrons. And, as an aside, I want to mention it is the number of protons that defines the element. So you can actually alter the number of neutrons, or you can alter the number of electrons, and you won't change it, right, from a carbon to something else. But if you change the number of protons, if you were to add a proton, you would no longer have carbon, okay? So if you were to add a proton, you no longer have carbon, you have nitrogen. If you removed a proton, you no longer have carbon, you have boron. So the atomic number, the number of protons, is what defines the element. Okay, so back to neutrons. So neutrons, typically, for most of these elements, the most abundant element will have the same number of protons and neutrons. So something called carbon-12 is by far the most abundant type of carbon on the planet, making up something like 98.9% of the carbon on the planet. But there are forms of carbon that we call carbon-13 and carbon-14 that actually vary in the number of neutrons. Carbon-13 has 7, carbon-14 has 8. These are called isotopes of carbon. And yes, 99% of carbon atoms are carbon-12. 1% of carbon atoms are carbon-13 or carbon-14. So we refer to these as isotopes of carbon, different forms of the same element. And each of these has, so they all have the same atomic number, right? The atomic number is 6 for all of them because they're all carbon, but the mass numbers will be different, right? This one, carbon-12 will have a mass of 12, carbon-13 will have a mass of 13, carbon-14 will have a mass of 14 because it's got more neutrons, it's heavier. So when we look at the atomic weight here, we see this funny number, 12.012. And that's because the number on the periodic table is representing an average of all the isotopes of carbon on the planet. Now you can see it's close to 12 because 99% of all carbon isotopes are carbon-12 and have an atomic mass of 12. So in terms of averages, we're much heavier weighted towards carbon-12. But we do have to take into account those other more rare isotopes. So that's why we end up with this funky number at the bottom of 12.012. Okay, we are going to take a break here. I'm doing, I want to do 3 or at least 2 or 3 shorter videos rather than one humongously long video like I did with chapter 1. So this is going to be the end of chapter 2, part 1, and we are going to pick up right here on the part 2 video. So bye-bye for just a few seconds, but I'm coming right back.